Okay, welcome everybody to the third lecture. So let me just recall a bit what we have still now learned. So we have actually learned three different definitions of defining curvature in something. So the first definition, what it said, like let sigma in R3 be a surface patch with standard unit normal n. Then the first definition was the second fundamental form. The second fundamental form was defined as L du square plus 2m du dv plus n dv square, where L is given by sigma uu dot n, m was given by sigma uv dot n, and n was given by sigma vv. Okay, this was the first definition. So then what we saw, we actually defined some Gauss map which sends the element like points of S to the unit sphere, like sending P to NP. And correspondingly, then we defined WPS, the Weingarten map. So from TPS to TPS as WPS minus dpg. Okay, so dp is just like the derivative of the Gauss map. So this was the Weingarten map, and then the second fundamental form was defined as the bilinear form as VW network PS as taking the normal inner product of WPS of VW, where VW were elements in TPS. Yeah, and this we have already seen that this definition and this definition, they gave same bilinear form. In other words, they were equivalent. Okay, so this we have seen. And then the final thing what we saw in the section of normal curvature, like you can define, one can define a normal curvature kappa n, and one obtains kappa n. You can think of it as the projection of gamma dot dot to the unit norm. So this we actually proved, but this you can take also as a working definition. Yeah. And then finally, what we ended last lecture with a proposition, which is going to show us that this definition also gives us the same fundamental. So what was the proposition? I will just rewrite it again and then prove it. So if gamma is a unit speed curve on an oriented surface S, then its normal curvature kappa n is given by the following, kappa n is actually inner product of gamma dot and gamma dot. So in other words, in particular, if sigma is a surface patch of S and you take a curve gamma t sigma ut pt in sigma, then essentially what I am getting is kappa n is nothing but L u dot square plus 2m u dot v dot plus n v dot square. So where L, m, n are as before, right? This is just this L, m, n. Yeah. Good. So that's the proposition we ended with, and let's try to prove this. So proof, it's actually not that difficult. So if you remember our construction as we have drawn the pictures, gamma dot, so as gamma dot is a tangent vector to S, we have n dot gamma dot, this is actually 0. So if you differentiate this by chain rule, then you get n dot gamma double dot is nothing but minus n dot gamma dot. Okay, this is just by chain rule. And now what you see that by definition kappa n, as I told you, I mean just here for example, this we can take as a working definition. So gamma n is n dot gamma dot dot, which is nothing but minus n dot dot gamma dot. And now let me do one thing. So what is n dot? N dot is nothing but d dt of the Gauss map of gamma t. And this is nothing but by definition the Weingarten map of W of gamma dot. That's just by definition. So essentially what I'm saying is, as this is true, this I can rewrite as inner product of Weingarten map of gamma dot with gamma dot. So what we get, kappa n is actually inner product of gamma y dot with y dot, and that's just by definition the inner product given by the second fundamental form. See, I mean, this definition, this is again, let me show you, that's just exactly the same thing I recalled before. And that's the definition of the second fundamental form. And since this one, this fundamental form is equivalent to this one, so this actually proves the proposition that, so this we already obtained, this is the equivalent definition to the second definition, and the second definition is equivalent to the first one, so this implies this. This is quite immediate. Any questions? Okay. So this actually finishes the proof. So we are done essentially. So what, let me again stress this again. So even if you define the normal curvature in this way, in the, according to the projection of this gamma dot dot to the normal component, then it also gives you essentially the equal amount of information of the curvature or equal amount of information from the curve. And finally, you should realize this is not surprising, right? Because if you remember the motivation behind every definition, essentially we are trying to see how the how the surface curves in some sense in a different manner, but ultimately it should all give the same definition, and which is the case. So we are not saying something extraordinary. It is what is expected, but it's good to know that we have been coherent with all the definitions. Good. So then let me give you some applications of this normal curvatures. So first, let's consider one definition. So if gamma is the intersection of the surface with a plane, let's say big gamma, yeah, with a plane that is perpendicular to the tangent plane of the surface at every point of the curve, then I will draw a picture, then it will be more clear. Then gamma is called a normal section of the surface. So what do I mean? Let me draw the picture. So you have a surface, and let's say you have a curve here, which you obtained as a intersection of some plane. And this is the normal vector. And what I'm saying is, so that's the plane which intersects. And what does the definition ask you? That this plane essentially, I mean, this plane, this is perpendicular to the tangent plane of the surface at every point of this gamma. I mean, that's the, so essentially at every point you have like a the tangent, the plane would be like a perpendicular to every point of this gamma and the tangent plane of the surface. I mean, so that's like the normal section in some sense here. Okay, so it's a very special case. I mean, that's, of course, for every surface it might not happen. That's why I have drawn the picture in some sense, which might give you some idea if this can happen or not. And of course, you should think that this is not going to happen, because for this we are going to get some nice results about the normal curvatures. Okay, so if you have a normal section, then that gives you the next corollary, which is very nice. So corollary, the curvature K normal curvature kappa n and the geodesic curvature kappa g of a normal section, they are related via these following formulas. Normal section of a surface, they are related by, so kappa n is nothing but plus minus kappa, and kappa g is actually 0. So what I'm saying, so if you have, let's show it again. So if you have a normal section like this gamma, it's an intersection of this plane and the surface, and at every point of this gamma, the tangent plane, I mean this pi, the plane what intersects the, this is perpendicular to the tangent plane at every, okay. If that happens, then the normal curvature is nothing but up to sine the curvature of the curve, and the geodesic curvature is 0. This you forget about this. I mean, this we are not that interested, but let's think about this. Why this is happening? I mean, let's check it again. If this is a curve, and now what am I asking? What I am asking is that at every point, the plane intersects at this point and the tangent plane, both of them are perpendicular. So in some sense, intuitively, the change as, I mean, how does the curvature is defined here? It's like the norm of gamma double dot, right? That if you remember, that's how I started up my lecture actually. That was the first definition. And since this perpendicular assumption is there, up to orientation, this is essentially the same thing of asking the normal, because what's the normal thing? The normal curvature is like projecting it to the normal, the unit normal thing. And since it's perpendicular, it's essentially you are projecting to the same thing. I mean, so then this condition is not that difficult to assume, but difficult to believe. But let's see the mathematical proof of it. So we already know this, I proved last lecture, that the kappa n, this is not only given by this formula, this is also, moreover, it's actually kappa sine theta, where theta was the map between the unit normal and the normal of the curve, right? Now that's exactly what I was saying in intuitively in the geometrical sense. So this theta now, by definition, so now by the assumption of the normal section, this theta is nothing but plus minus 90 degree, yeah. So for a normal section. That's exactly the definition. And this implies Kn is plus minus kappa. And once the normal section is plus minus kappa, then this gives you the Kg is 0. Why? Because if you remember the relation, kappa squared is nothing but kappa n squared plus kappa this. Right? So this finishes the proof. So essentially what you are saying, if you have a normal section, then the normal curvature and the curvature of that curve, both of them are equal up to sine. And this sine you can always determine with the orientation. Is it clear? I mean, okay. I don't hear any complaints, so I will assume it is clear. Okay, so this is one application, and then there is another application which is a bit long actually to state the theorem, and then this I have actually drawn the picture already earlier. Do this in this way. So let me first write down the corollary first. So sometimes this is called Moniers Theorem. So he was a French mathematician, and he also, he also have actually a very nice history, because he was one of the army general of Napoleon Bonaparte. So with doing mathematics, he was a very famous army general also. Yeah, but anyway, let's focus on what he says. So let P be a point of a surface S, and let V be a unit tangent vector to S at P. This is a very long statement, but please bear with me. I will again draw the picture, so I hope it will be clear. It's not that difficult, just you have to assume many things. So let pi theta be the plane containing this point and which is parallel to V. So let pi theta be the plane containing the line through P and parallel to V. So simultaneously, let me draw this. So you have a surface. No, just a second, let me. This is going to be a big picture, so let me draw this here. So let's this be a surface. This is surface S. And what I'm assuming, let this be a point P, and let this be the unit vector, tangent vector to S at P. And then what I am assuming, so accordingly, then let me consider this as the tangent plane. Okay. And now let me just give this as dot dot so that you. Okay. So that's the tangent plane, and then you have this as here, and then finally what you consider the plane through here and through here. So it's like this, because that's how you will get the parallel plane. So that's pi theta, like big pi theta. Okay. And what you get is this curve, what you obtained this you say as gamma theta, like the curve you obtained as an intersection of the plane pi theta and s. And this map is actually theta. So the intersection angle between the plane pi theta and the tangent. Okay, so that's why I need to write so many things. Yeah, but just bear with me. So let pi theta be the plane containing the line through P which is parallel to V. That's what exactly I have drawn. And then, yeah. Yeah, sorry.
Pi theta passing through V. Huh? Why
Yes.
parallel to V? You mentioned that. Why we mentioned that parallel to V?
Oh yeah, that's my drawing error. So because when I am when I'm writing or drawing this, this is you should think of this as like in 3 dimension. So this is the tangent plane. So this V is essentially like you are putting on the surface. I mean, you should consider this 3D. So in some sense, this plane and so it's like the notion is in such a way the parallel in the direction in some sense. I mean, it's not like B. I mean, I don't know if I made it clear or even more confusing. So it's like the V is the unit vector, right? And this TPS, that's the TPS. That's the tangent plane. And so essentially, if theta is then 90, then this pi theta essentially is like perpendicular to the TPS. And then it's like perpendicular. So the parallelness assumption is not like you are saying it's crossing through or not. That's not the case. It's like the direction is parallel.
Okay.
Is it? Yeah, yeah, okay, yeah. Yeah, I did not say, I mean, yeah, that's my I guess bad wording, but yeah, and bad drawing also, but yeah, but you should think of direction as bad. Okay, and it has what I already drawn. It has an angle theta with the tangent plane TPS. So now assume pi theta is not parallel to TPS. So you should not, I mean, theta is not 0 in some sense. I mean, what I'm saying. And pi theta intersects S in a curve with curvature kappa theta. So what I'm saying is you are assuming the curve obtained by the intersection, which is gamma theta. So the curvature of that curve is kappa theta. Then the statement of the theorem says, then this kappa theta and sine theta, if you take the product, this is actually independent of theta. So let's come back here again. So whatever angle you make here, I mean, as long as it's not parallel, and this is gamma theta, and for gamma theta you have kappa theta, and kappa theta sine theta, if you take the product of these two, whatever you vary the theta, this is independent of theta. Okay, that's the content of the theorem. And it's why this is the case, it's due to very simple reason, because this kappa theta sine theta, this is nothing but the normal curvature of this normal curvature of the surface at this point along this curve actually. So if it is a normal curvature, then it's not dependent on theta, it depends only on P and the unit tangent vector. So essentially, if you rotate this phi theta, if you rotate a bit, then the curvature of this guy it remains the same. That's like the proof also. So, but let me give the formal proof. So proof, assume gamma theta is unit speed without loss of generality. Otherwise, you can take the unit speed parameterization, which is also unit speed parameterization. Then, by definition, gamma theta dot, this is nothing but plus minus v, because that's the tangent, I mean, unit tangent vector. That's by definition. So what I'm saying is this implies that gamma theta double dot, this is actually perpendicular to v and parallel to pi theta. Because since it's perpendicular to v, then, and since the pi theta is parallel to v, so then it's parallel to pi theta. So that's okay. So in particular, if this is the case, then if you remember the definition psi, the psi was the angle what we obtained with the normal unit normal vector for the definition of normal curvature. So essentially this psi is nothing but the 90 degree minus pi by 2 minus theta. So I mean, let me see. Yeah, for example, when we had this, I mean, with this psi, actually, we would have this formula. Actually. Okay, so this formula, Kn was kappa sine theta. This theta was actually in the proposition psi. So I'm just naming this psi. And this psi would be actually pi 2 minus theta. So in other words, with the same proposition, then the normal curvature, this would be this k theta. K theta is the curvature of this guy, sine theta. So as I was now saying, as kappa n, but this is the normal curvature. As kappa n depends only on the point P in S and the unit normal, I mean the unit tangent vector V, so then we are done essentially. So let me show it again here. So this was theta, and if that's what I stated, if this was perpendicular to this plane, that's pi by 2. So somehow the other part is here, if there was some another plane here, this angle somehow it's pi by 2 minus theta, and that's the psi which appears in the definition of the normal curvature. And then you just by the proposition you get Kn is k theta sine theta. So it's a very long way to say some simple thing. So essentially what I'm saying is, if you define it, this actually appeared in some other geometric notions. I mean, that's why this seems very out of nowhere, but it had some other backgrounds. But ultimately, it's a very nice thing, because here it appears that this theta should contribute to the, I mean, when you write k theta sine theta, there is apparently no reason that why this should be independent of theta. But it is because it somehow equates with the normal curvature cut out by this curve and at this point along with this P. Okay. Yeah. So as I was telling, this is sometimes called as Moniers Theorem. And then let me finally end this section with a proposition which is called Gauss equations. So this is the first instance where you would see the interaction between first and second fundamental form. So what do I mean? So let me write this down. So let sigma uv be a surface patch with first and second fundamental form as E du square plus plus 2f du dv plus g dv square, and second fundamental form is given by an L du square plus 2m du dv plus n dv square. Okay, so if you have these two as a input, then you actually have some series of equations which are like sigma uu is gamma 1 1 1 sigma u plus gamma 2 1 1 sigma v plus l n, and sigma uv is gamma 2 1 1 sigma u plus gamma 2. Sorry, not the same. It's like a matrix coefficients. I mean, it's nothing. 2 sigma v plus m times n. These n's are the unit normals. Okay, that's why I'm putting it in bold. And sigma vv is sigma 1 2 2 sigma u plus sigma 2 2 2 sigma v plus n times n. So let me point this out. This L, M, and N, these are the coefficients in second fundamental form. And now then you should ask, what are these coefficients, right? I mean, these 6 coefficients. So these 6 coefficients, they actually are dependent on this F, G, and E. So let me write this down. I will not write down all the formulas because these are just tedious formulas. So where I will just write down the first 2 coefficients, like this one and this 2. I mean, the first 2 for sigma u and sigma uu. So where sigma 1 1 1 is given by g e u minus 2 e f u plus f e v given by 2 eg minus f square. And you would see this eg minus f square, you should think of this kind of a determinant, right? I mean, these things again you will see again in the next lecture also. And gamma 211, this is given by 2 efu minus EFV minus FEU by 2 EG minus F square. Okay, and so on. So let me just remark quickly. These 6 coefficients, they are actually called Christoffel symbols. Okay, so you would have for this kind of expression for not only for these 2, also for these 2 and also for these 2. So there are total 6 symbols. That's why I'm telling you about these 6 coefficients. And they will be actually important later to determine some nice global properties. So one thing you should immediately see, if you only check this one or this one, that they only depend on first fundamental forms, right? And the second fundamental form coefficients are kind of the last coefficients here. Okay, and then another side remark, actually, these Christoffel symbols, they are very important in many different areas also. So for example, in Einstein's general theory of relativity, they have a very prominent use. And so I'll just remark frequent use in Einstein's general theory of relativity. Why this is the case? Because what happens in general theory of relativity, also you consider four-dimensional manifold, which is like a generalization of R3, and then there also you need to find out the curvature of like the space-time curvature, and those are actually given by somehow of these properties. I mean, this will reappear again in the next lectures. Good. So you should not be really scared about these whole formulas. I mean, let me just prove one of them, and you would see this is really kind of basic actually. So how does one prove this? So first, consider the sigma u, sigma v, and the unit normal n as a basis of R3. Okay. So since this is a basis, you can find the scalar extension. I mean, like there exists scalars such that the sigma u, this will be nothing but a scalar combination of these three. So that's exactly what, let me write. It's simple linear algebra actually. And similarly, uv will be, let's say, beta 1 sigma u. You can also write it in a better notation, I think, in matrix notation. I'm just following the book's notation. Sorry, these are v's. Plus beta 3n. And similarly, sigma vv is, let's say, gamma 1 sigma u plus gamma 2 sigma v plus gamma 3. So let me first take dot product of these equations with n. So if you take dot product with n is like the unit normal, right? So if you take dot product with n, all these things will be 0. So then what you get? You get alpha 3 is nothing but sigma u dot n. But what is this? By definition, this is the first coefficient of the second fundamental form, right? This is L. Correct?
Yes.
Yeah. So similarly, you get beta 3 is nothing but sigma uv dot n, which is nothing but m, and gamma 3 is nothing but sigma vv dot n, which is nothing but n. So you already proved the this part actually. So this is already proved. The coefficients you have already determined. So I will determine these two. It's again in a similar technique. So what I will do now, I will take dot product with, let's say, only first equation, with the first equation by first by sigma u and then by sigma v. So then if you just take this, let's see what happens. So if you take dot product with sigma u, then sigma u dot sigma u, what is that? That again, by definition, it's the first coefficient of the first fundamental form. And sigma u dot sigma v is the second coefficient of the first fundamental form. So essentially what you get, so you get E times alpha 1 plus F times alpha 2 this is nothing but sigma u dot sigma u, which is nothing but half EU. Because that's again by definition. And similarly, if you take the dot product with sigma v, then you get f alpha 1 plus g alpha 2 is sigma u dot sigma v is actually, you can again compute fu minus half epu. So now you have a linear series of equation of alpha 1 and alpha 2. So you can just solve it as a linear equation. And exactly if you do this, then this will give you the expression of alpha 1 will be gamma 1 and alpha 2 would be gamma 2. So that's why now let me show you the expression again. Yeah, see, these are the terms here coming here. And why this eg minus f square is coming? Because if you remember the linear algebra part, the inverse of a matrix is given by the, you have a, in the denominator you have the determinant, right? So this is the determinant, this is appearing, that's why. So when you want to resolve this, then what's the matrix? The matrix is E, F, F, G. And what's the determinant of this? This is exactly the same. So you have to proceed and then you can prove this. So, I mean, let's just think, I mean, a bit for this for a second. I mean, so essentially you obtained a nice relation between the, let's say, L and the F, G, and E, all these things. So it's kind of how the first and second fundamental form interact in some sense. So this might seem now very abstract, but this is going to be used actually in one of our final theorems in the Gauss remarkable theorem and stuff. Good. So yeah, this was essentially not exactly related with normal curvature, but I just wanted to be included here because now okay, I have some few more minutes because I started 5 minutes late. So let's go to the next section. So this is called Gaussian and mean curvatures. So let's now think a bit again what we have successfully obtained. So if I just make a summary of the previous section, the whole, I mean, almost 3 talks we have learned is, so we have learned 3 different definitions of second fundamental forms and their properties. Good. So once somehow we are convinced that we have understood many different ways of finding out the curvature, then the next job is to find out some geometric information from the second fundamental form or its Weingarten map. And that's exactly what we will do in this section. So again, recall, we have this map W, which is WPS, as a map from TPS to TPS, where P is a point where P in the oriented surface S, a point, and S an oriented surface. So this we have. Now note this W, this is a linear map. in fact, if you remember last talk, this was not only linear, this was also self-adjoint, which is a quite strong property for a linear map, right? I mean, if it's also self-adjoint, then it has some nice properties about eigenvalues and stuff, which also will come in the next lectures. But now, first, let's consider this as a linear map. So once you have a linear map, then you know that as a linear map, then you have a matrix associated to the linear map, right? And once you have the matrix associated to the linear map, then there are two invariants, what you can immediately compute. So what are those? Those are like the determinant and the trace. And that's exactly my next definition. So the Gaussian curvature, which people call it K, and the mean curvature, which people call is H, of S at P is given by, as I said, you define K to be the determinant of the linear map and H to be half of trace of this linear map. So this we can do, right? I mean, since this is a linear map, we can define a determinant. How do we do this? You find some basis along with around that basis, you have a matrix associated to this linear map. And then you, for the matrix, you compute the trace, you can compute the determinant. And this is, of course, independent of basis. All these things you know, right, from linear algebra. And let me just remark one small thing. So remark. We have a favorite basis, right? What we can take. It's about using the tangent vectors. So one can take the tangent vectors as basis. And then let me make another remark. So when the, because if you remember here, I have taken an oriented surface. So whenever you define something for only an oriented surface, the next natural thing is to consider, if you remove this assumption, what happens? So what I am asking is, if the surface is not oriented, if it changes the orientation, then what happens? Is the definition well defined up to orientation, or is it maybe defined up to sign? So that's the remark. So when the orientation changes, or like when the sign of n is changed, then the Weingarten map also changes sign. This actually you would do as an exercise in, I hope, in the tutorial, that when the sign is changed, the Weingarten also changes sign. But still, the matrix of the matrix associated to the linear map, this remains, I mean, when you take the determinant, this remains unchanged. So what I'm saying, one can show that even that this K remains unchanged. So in other words, K can be defined for any surface, oriented or not. But one would see some appearance of sign for the mean curvature. So H is actually defined up to sign, which is okay. Even when you have a definition up to sign, then also you can determine the sign. So I have 5 minutes left. So let me see if how far I can go. So then the next thing is this formula. When we defined it, I mean, this is not actually a formula. This is just the definition. It's really not an explicit thing, right? So we should somehow find the explicit description of this determinant. And then as I have already given you the hints, how should we find out the explicit expressions? It's about you write the linear map in terms of the basis vectors, and we will take our favorite basis vectors with the tangent vectors, and then let's see if we can find something with the relation from first and second fundamental from coefficients. And that's exactly the next proposition. So let sigma be a surface patch on an oriented surface S. Then you define two matrices, Fi, which is for the first fundamental form. This matrix I was already telling you, EF, FG. And you define another matrix for the second fundamental form with the coefficients L, M, M, N. Then the matrix of the Weingarten map with respect to the basis of tangent vector sigma u sigma b of the tangent plane is nothing but Fi inverse Fi. Okay, so let me just write this down, what I am saying. So you have the first fundamental form, right? You have first fundamental form as E du square plus 2f du dv plus g dv square. And here you are defining Fi as the matrix E, F, F, G. So this is a symmetric matrix, right? And you also have the second fundamental form, which is given by L du square plus 2m du dv plus n dv square. And here you define Fii is E, sorry, L, M, M, N. This is also symmetric matrix. And now you have the Weingarten map from TPS to TPS. So you are saying the matrix of this linear map, this is nothing but Fi inverse Fi. Okay, so that's the content of this proposition. So yeah, so the matrix given, matrix of the Weingarten map is given by Fi inverse Fi. So I will actually stop there because I am now running out of time, but tomorrow we'll prove this, and then we'll see how this proposition will actually give us a very nice expression of the Gaussian curvature and also about the mean curvature. And then we would compute some nice examples and see how this gives some global picture or global information about the things. Yeah, okay, I'll stop here. So any questions?